Good evening, everyone. I would like to welcome you all to the sixth session of S.Eng's training series. Today we have Dr. S.K. Ghosh, who needs no introduction. He will be presenting the first among the 9 concrete courses today, and he will introduce us to material aspects of concrete in today's webinar. I see that we have already got 800 and more than 870 participants. So, Dr. Ghosh, do you think it is the right time to start?
Let's do it at 8:05 to maximize the number of people here, I think. Okay. Exactly at 8:05 we'll start.
Okay, sounds good.
Thanks.
Once again, I would request everyone that kindly don't join from multiple devices. So if the webinar is working in one of your devices, then try and then log out from the other device. That way, other people who are waiting, they can join in. Because one thing that I observe is that the date it is showing as 10th January.
Oh, that date wasn't changed yet.
Yeah.
Okay.
Somehow we missed it. Yeah.
Before you, I don't know if it is worth trying to do it now.
Yeah, it's fine. That's fine. Yeah. So
Okay, good evening once again. It's 8:05, so let us start. Bodhi has already provided a bit of an introduction, so I'll just go forward. He has pointed out that the date is 11th of January, not 10th. We had to make some adjustments at the beginning of the program because of circumstances beyond our control. So today is the sixth offering in the series, and we are starting with our reinforced concrete courses. Today is a two-part course. I'll talk about the material aspects of concrete and then go on to strength design, the principles of strength design, what it is that we do when we do strength design of concrete. The ingredients of concrete, as you all know, are cement, sand, stone, and water. Those are the basic ingredients. But for a long time now, we also have admixtures in concrete. Admixtures used to be classified as mineral admixtures and chemical admixtures. Mineral admixtures will be something like blast furnace slag or fly ash. Those are now called supplemental cementitious materials, and the chemical admixtures are called admixtures. Cement plus the supplemental cementitious materials are called just cementitious materials. So what used to be water to cement ratio today is water to cementitious materials ratio. However, the code that we are talking about, BNBC 2020, as pointed out earlier, is based on ACI 31808. Back then, it was still water-cement ratio, and that is the terminology that you will see as we go forward. Okay. Now, in addition to all of this, we have reinforcement in concrete. That is because concrete is reasonably strong in compression, but it is weak in tension. If you stretch on a piece of concrete, you don't have to go too far because the concrete cracks. And when it cracks under tension, that is pretty much the end of the story. It fails. It cannot take any more tension beyond that. So we typically combine concrete and reinforcing steel in the same structural member, the concrete carrying compression, the reinforcing steel carrying tension. That gives us reinforced concrete. And the reinforcement is something we need to talk about. What kind of reinforcement that do we have in concrete? Reinforcement, again, is basically in two categories: reinforcing steel and pre-stressing steel. There is now reinforcement that is not steel reinforcement, but overwhelming majority of the cases we are talking about reinforcing steel as reinforcement. The concept of pre-stressing is we put the concrete under compression before any loads come on our structural member. And the idea is then until this pre-compression is overcome by tension, the member is not going to crack or fail. There are two different ways of applying this pre-compression on the concrete. Both involve pre-stressing steel, and that's also something that we will talk about just a little bit. Okay, so again, the ingredients of concrete are cement, sand, stone, and water. The stone is called coarse aggregate. The sand is called fine aggregate. In addition to the items I mentioned, we have admixtures in concrete. Admixtures can be mineral admixtures or chemical admixtures. Mineral admixtures are now called supplemental cementitious materials. Supplemental cementitious materials together with cement constitute cementitious materials. Okay. Reinforcement is typically in the form of reinforcing steel, or it can be pre-stressing steel, and those are the ingredients that we will talk about in the first part. So the standards, the documents that the ingredients of the concrete have to comply with are given in Chapter 3 of ACI 31808. It's one chapter organized pretty simply. All the reference standards like ASTM specifications that we have to comply with are listed in that chapter. In BNBC 2020, it's a more complicated arrangement, and this is why I thought I would start here with this slide. So most of the information that I'm going to present here and you have to look for are in Volume 1, Part 5, titled Building Materials. And within Volume 1, Part 5, there is Chapter 2, also titled Building Materials. Section 2.3 is on cement and concrete. That's where most of the information that I'm going to present is to be found. But there is some information also in Volume 2, Part 6, Structural Design. And in Volume 2, Part 6, the chapter that you have to go to is Chapter 5, titled Concrete Materials. So these are the two places where you have to look for information on the ingredients of concrete. Which documents do you have to comply with? So this slide is on cementitious materials, which you understand include cement and the supplemental cementitious materials, which were the mineral admixtures. Okay. So cement in Bangladesh complies with BDS Bangladesh Standard 197-1. Okay. I am told that virtually all cement sold in the country is BDS 197-1 cement. Now, also permitted are ASTM C150 Portland cement, blended hydraulic cements, C5 ASTM C595, hydraulic cement ASTM C1157. I will show you briefly what those cements are. And then among the supplemental cementitious materials, fly ash and natural pozzolans, ground granulated blast furnace slag. So the ASTM standard for fly ash is C618. The ASTM standard for ground granulated blast furnace slag is C989. And then in Part 2, Chapter 6, we also have listed sulfate resisting Portland cement BDS 612 and Portland cement BDS 232, which are apparently not used. Silica fume is recognized in ACI 31808, but it is not in BNBC 2020. That is another important mineral admixture that you need for high strength concrete. Now, to go back for a second, as I said, basically all cement sold is BDS 197-1, but it is tested for compliance with ASTM C150. And when tested, BDS 197-1 cement is found to comply with ASTM C150. That's pretty much the situation as I understand it. Okay, so Portland cement, then blended hydraulic cement C595, hydraulic cement C1157, and the mineral admixtures, among which fly ash and natural pozzolans and ground granulated blast furnace slag. This is what we are dealing with for concrete making. The BDS 197 cement comes theoretically at least in 5 varieties. Chem 1 is Portland cement, Chem 2 is Portland composite cement, Chem 3 blast furnace cement, Chem 4 pozzolanic cement, and Chem 5 composite cement, meaning cement and pozzolan together. Now, Dr. Akif tells me that pretty much all cement used is Chem 1 and Chem 2. Chem 3 has been used in nuclear power plants, and that 4 and 5 are basically not used. C150 Portland cement, this is this is the American standard that is followed throughout the United States and in some parts of the world. So C150 cement also comes in 5 types: type 1, type 2, type 3, type 4, type 5. 1 is normal, 2 is moderate, sulfate resistant, very important. If there is sulfate in the soil, you may want to go for type 2 cement. Type 3 is high early strength. I think the name tells you what it is. Type 4, low heat of hydration. So as cement reacts chemically with the water, there is heat generated. And that may cause problems depending upon what you are doing, how you are curing the concrete, and so forth. So in many applications like mass concrete, low heat of hydration may be an attraction. And then high sulfate resistance. When type 2 Portland cement on do, you need type 5, high sulfate resistance, cement with high sulfate resistance. And then for types 1, 2, and 3, there is air entrained cement. Entrainment of air in the cement is for freeze thaw resistance. You do not have that problem in Bangladesh. But in much of the US, the entire northern part, concrete freezes and then thaws and then freezes again. That causes a lot of damage. And to alleviate that damage, air is intentionally entrained in concrete. That typically is done by adding air entraining admixtures to the concrete mix, but sometimes air is entrained in the cement itself at the cement plant, and that gives us the type 1A, type 2A, and type 3A Portland cements. You don't have to worry about air entrainment to the best of my knowledge. The blended cements C595, that is type 1S, which is Portland blast furnace slag cement, and 1P Portland pozzolan cement. The 1S, if you have 1S parenthesis 50, that means the blended cement contains 50% slag by mass. And if it is a 1P cement, then within parentheses, you may have A for air entraining, MS for moderate sulfate resistant, and so forth. So C595 blended cement is type 1S or 1P with additional information that is conveyed through the labeling. 1157 hydraulic cements, this is relatively new. C150 goes back a long way, then came 595, and then 1157 is relatively recent. This is also called performance spec, meaning the ingredients and so forth are not pinned down, but what properties the cement will deliver is the is emphasized. So hydraulic cement C1157 can be type GU, general use, HE, high early strength, MS, moderate sulfate resistant, HS, high sulfate resistant, MH, moderate heat of hydration, LH, low heat of hydration. So this kind of mirrors the varieties of C150 Portland cement that we have. Fly ash, probably the most common mineral admixture that is used in concrete. Fly ash gives the concrete a very dark color, but fly ash itself is not dark, as you see in the picture. The ASTM spec so the fly ash that you use must comply with ASTM C618. That is the ASTM spec for coal fly ash and raw or calcined natural pozzolan for use in concrete. So C618 for fly ash. Ground granulated blast furnace slag, that again is a pretty popular mineral admixture or supplemental cementitious material. The ASTM, applicable ASTM standard is C989, standard specification for slag cement for use in concrete and mortars. Okay. Now, this is not citing a standard, and this is a requirement in all the slides. In the section numbers in black are 31808 section numbers. The section numbers in blue are BNBC 2020 section numbers. Okay, so both documents tell you cementitious materials used in the work, meaning project, shall correspond to those used as the basis for selecting concrete mixture proportions. Okay, so you proportion your mix assuming that you are going to use certain supplemental cementitious materials. On the project, you have to use exactly those materials, not something close to those, etc., etc. Okay, so I think this is understandable upon reading, but this is very, very important. Whenever we have on the slide text in this color, that means it is ACI 318 text that does not appear in BNBC 2020. We go from cement to aggregate. Concrete aggregate shall conform to one of the following specifications. BNBC 2020 says coarse and fine aggregate shall comply with BDS 243. Okay? So coarse and fine aggregate from natural source for concrete, BDS 243. The US specification for normal weight aggregate is C33, and for lightweight aggregate it is C330. So C33 is normal weight aggregate, C330 is lightweight. BNBC has an exception that reads aggregates that have been shown by special test or actual service to produce concrete of adequate strength and durability and approved by the building official. Those do not have to comply with ASTM C330. Or in other words, you may use lightweight aggregate that is not in compliance with C330 if as the exception says, it has been shown by special test or actual service to produce concrete of adequate strength and durability, the aggregate that you want to use, and it has been approved by the building official. Okay, this is a requirement both of ACI 318 and BNBC 2020. Concrete aggregates shall conform to one of the following specifications. So this is all blue. That means we do not have these in ACI 31808, but you have them in BNBC 2020. Aggregates for radiation shielding concrete, ASTM C637. Lightweight aggregate for insulating concrete, C332. Artificial lightweight aggregates for concrete masonry units. That's IS, that is an ISO standard, International Standard Organization Standard 9142. This is not an ASTM. So those are cited by BNBC 2020, but not ACI 318. I realize that this is not exciting stuff, but these things are important. All the ingredients of concrete have to comply with applicable standards and specifications. The next slide also has something extremely important. Nominal maximum size of coarse aggregate shall not be larger than. So nominal maximum size, nominal means it is not the measured number, it is what it is claimed to be. So nominal 3/4 inch aggregate may be smaller when you actually measure it in size. A nominal maximum size of coarse aggregate shall not be larger than 1/5 the narrowest dimension between sides of forms, 1/3 the depth of slab, and 3/4 the minimum clear spacing between individual reinforcing bars or wires, bundles of bars, individual tendons, bundle tendons, or ducts. Tendon would be pre-stressing steel strand, things of that kind. So the whole purpose of this is that concrete can be placed, that there will not be voids in the completed structural member. This is extremely important. If your stone pieces are too big, then voids may very well be created in the concrete because the concrete does not flow. It does not fill all the gaps that need to be filled. So 1/5 the narrowest dimension, etc. You can read this. This is extremely important. You cannot always use large aggregate, obviously. Okay, aggregates for concrete. As mentioned, BDS 243 is the standard coarse and fine aggregates for natural sources for concrete. C330 is the standard or specification for lightweight aggregate. The title is Standard Specification for Lightweight Aggregates for Structural Concrete. Mixing water for concrete. Mixing water is more important than anyone would think. I would say extremely important that the water that is used in mixing concrete be non-problematic water, let me say. We now have an ASTM C1602. It's relatively new. I haven't checked back. I suspect that when 31808 came out, that specification was simply not available. So that is not cited in BNBC 2020. Okay. So BNBC 2020 says mixing water for pre-stressed concrete or for concrete that will contain aluminum embedments, including that portion of mixing water contributed in the form of free moisture on aggregates. So free moisture on aggregates shall count as mixing water. That is important. Okay, so mixing water shall not contain deleterious amounts of chloride ion. And how much is deleterious is given in both BNBC and ACI 31808. For that, you have to go to section 553. Okay? So mixing water for pre-stressed concrete shall not contain deleterious amounts of chloride ion. this is the important part. Okay, so BNBC 2020 does not cite a specification or standard for mixing water, but it very importantly says, has this section 5233 titled non-potable water shall not be used in concrete except the following conditions. So this is a non-potable means non-drinkable. Water that you cannot drink must not be used in concrete making. This is the simple rule. Water that you cannot drink shall not be used in concrete making. As simple as that. Okay? So there are a couple of exceptions. Selection of concrete proportions shall be based on concrete mixes using water from the same source, and non-potable water is permitted only if specified comparative mortar test cubes made with non-potable water produce at least 90% of the strength achieved with potable water. So you are allowed to use non-drinkable water if you would make mortar cubes out of drinkable water and the non-drinkable water that you want to use, and the mortar cubes made using the non-drinkable water produce at least 90% of the strength produced by the mortar cubes made with drinkable water. Okay, under those circumstances, you will be allowed to use non-drinkable water in concrete making. Now, this is what is on this slide is I would emphasize extremely important. Okay, so and item A is also important. Selection of concrete proportion shall be based on concrete mixes using water from the same source. Now we go on to reinforcement for concrete. The first item is on not reinforcement, but welding of reinforcement. Welding of reinforcing bars shall conform to AWS American Welding Society D1.4. Okay. And I think the rest of it, I will let you read. It gets a little too much. Anyway, deform reinforcement. That's what we always basically use. There used to be plain reinforcement a long time ago, but that has now been discontinued for quite a while. So all reinforcement is deformed reinforcement. The deformations are those ribs that you see on reinforcing bars. It is also called ribbed bars, the deformed bars. So deformed reinforcing bars shall conform to the requirements for deformed bars in one of the following specifications. The specifications in Bangladesh are BDS 6935-1 and BDS 6935-2. -1 is plain bars, so those are not used. -2 are deformed bars, those are the ones used. So just as I remarked about cement, about reinforcement, basically all reinforcement used in Bangladesh, I understand, is BDS 6935-2. Okay. Now in the US, the vast majority of reinforcement is ASTM A615, but particularly in seismic applications, and I would say increasingly, we have A706 reinforcement. The difference between the two, A706 is weldable reinforcement, A615 is not. A615 reinforcement requires special treatment if we are going to weld it. The ingredients of A706 are also tied down much more strictly than those of ASTM A615. Okay. So ASTM A615 is standard billet steel, and A706 is weldable reinforcement. I understand that BDS 6935-2 reinforcement is tested for compliance with ASTM A615 or ASTM A706. It basically all pass the ASTM A615 specifications. Increasingly, apparently, manufacturers are testing 6935-2 reinforcement for compliance with A706. And there is apparently some material on the market that does comply with ASTM A706. If something complies with A706, it will automatically comply with A615. You don't have to do a separate set of tests. Okay. So then there is rail and axle steel A996. To the best of my knowledge, it is hardly ever used. And then A706, as I mentioned. BNBC 2020 also mentions a number of other items. IS 1786 cold work steel bars, rail steel 616, axle steel 617. The 616 and 617 have been combined into A996. So you are looking at the same American rail steel and axle steel. Okay? Because BNBC 2020 is based on ACI 31808. It cites the old standards rather than the new 996. It used to be 616 for rail steel and 617 for axle steel. And then galvanized bars A767 and epoxy coated bars A775. Yeah. Stainless steel is recognized in 31808, but not in BNBC 2020. Dr. Rakib tells me that epoxy-coated reinforcing steel is used in Bangladesh, particularly in coastal areas for basements and things like that. I'm talking about building applications. Those have applications in pavements and so forth. But other than that, the other stuff, rail steel, axle steel, cold work steel, those are not used. So 6935-2, which complies with ASTM A615, some of which complies with A706, is the predominant reinforcing material in Bangladesh. Now, continuing with reinforcement for concrete for bars with F sub Y exceeding 420 MPa. So that is 60 KSI. For bars with yield strength exceeding 420 MPa, the yield strength shall be taken as the stress corresponding to a strain of 0.35%. Okay. I think I have a yes. So ASTM definition of yield strength is as you see in the picture. Okay. We take 0.2% strain along the x-axis. We draw a line parallel to the initial elastic branch of the stress-strain diagram. Wherever it hits the stress-strain diagram gives us the yield strength F sub Y. Now, if the yield strength exceeds 60 KSI, then we are saying do not use that definition of yield strength. Your definition of yield strength is now the stress corresponding to a strain of 0035 along the x-axis. So this figure, now that I notice it is wrong, it shows 003, it should be 0035. Okay, so you take a strain of 0035 along the x-axis, the corresponding stress is the yield strength. So when the yield strength exceeds 60 ksi, the yield strength shall be taken as the stress corresponding to a strain of 0.35%. This change of definition of yield strength becomes important in certain applications, and it may come up in later discussions, but that is not the subject today. However, I do want to point out that this change of definition is made. Yield strength means different things for reinforcing steel up to 60 ksi yield strength and reinforcing steel with yield strength larger than 60 ksi. Then, in addition to bars, there are bar mats for concrete reinforcement. The applicable ASTM standard is A184. When I have M following the standard number, that simply means metric. Reinforcing bars used in bar mats shall conform to 615 or 706, though those are the two US specs for reinforcement. Now we go from bar to wire for reinforcement. So deformed wire for concrete reinforcement shall conform to A496. BNBC says shall not be smaller than size D4. I will talk about wire size on the next slide. Shall not be smaller than size D4, which has a nominal diameter of 5.72 millimeter. And for wire with a specified yield strength exceeding 410 MPa, F sub y shall be stress corresponding to a strain of 0.35%. So for the reinforcing bars, I said 420, here it is 410. It's basically the same thing, 60 ksi. The definition of yield strength changes. Okay, so ASTM A496 is the spec for deformed wire. Now, wire size, when we say D4, what does it mean? Individual wire size designations are based on the cross-sectional area of a given wire. M stands for metric, W represents plain wire, and D represents deformed wire. The number following the W and the D represents the cross-sectional area of the wire in millimeters square. Okay, so D4 means deformed wire having a cross-sectional area of 4 square millimeters. A D10 wire would indicate a deformed wire having a cross-sectional area of 10 square millimeters. Okay. So keep that in mind when you come across wire sizes. Then there is what used to be called welded wire fabric. Now it is called welded wire reinforcement. People who manufacture these do not like the term fabric. Now it is welded wire reinforcement. So welded wire reinforcement may be made of plain wire or deformed wire. So welded plain wire reinforcement shall conform to ASTM A185, except that for wire, again, for high strength exceeding 60 ksi yield strength, the definition of yield strength changes. Welded intersections shall not be spaced further apart than 300 millimeters, 12 inches, in direction of calculated stress, except for welded wire reinforcement used as stirrups. So there is a maximum distance, maximum spacing between the cross wires, okay, no more than 12 inches. Welded deformed wire reinforcement, the spec is A497. Again, the definition of yield strength changes when yield strength exceeds 60 ksi. Welded intersections shall not be spaced further apart than 4. So if it is plain wire reinforcement, the cross wires cannot be further apart than 300 millimeters. For deformed wire, it is 400 millimeters. Then there is galvanized reinforcing bars, 767, galvanized means zinc coated, that is protection against corrosion, or epoxy coated reinforcement. A775. Epoxy coated, as I said, is very popular in highway construction for pavements and in Bangladesh, apparently in coastal areas for basements and things because of the high risk of corrosion. This language is in ACI 31808, not in BNBC 2020. I think I'm going to skip it because of that. Okay, but if you have an interest, please read it. Okay, so we come back to reinforcement for concrete, plain reinforcement. You know that it is 6935-1. That's the plain wire for spiral reinforcement shall conform to, so plain bars shall conform to 6935-1 as mentioned previously. Plain wire for spiral reinforcement shall conform to ASTM A82, except that for wire with F sub y exceeding, so that definition of yield strength change repeats itself. This is something I will mention because I consider it to be extremely important. At some point, I don't remember which module now, we will talk about flat plate design. Flat plate is a reinforced concrete slab supported directly on columns. There are no column line beams. Also, there is no local thickening of the slab on top of the columns. Those thickenings are called drop panels. Further, there are no column capitals. The column tops are not flared to give us a larger column area at the top. So it is a slab supported directly on columns without any drop panels or column capitals. In the design of that type of slabs, the critical thing is punching shear, two-way shear as opposed to one-way shear, commonly referred to as punching shear. When punching shear stress is beyond the punching shear stress carrying capacity of the concrete, we use punching shear reinforcement. And the most popular kind are now headed studs. So there is a rail, a strip of metal with those studs welded to the metal strip. The head of the stud is much bigger than in the typical Nelson studs. These are big heads which anchor the studs to the concrete, and if properly anchored, those legs of the studs resist shear. Okay, so this is now by far the most popular punching shear reinforcement throughout the United States and in many countries of the world. Okay. Back in ACI 31808, it was already recognized. Prior to that time, the welded wire, the headed studs were a proprietary item. And we do not ever refer to proprietary items in ACI 318. But that has changed a long time ago. We have brought the headed stud reinforcement into ACI 318, but somehow, probably because it's not available in Bangladesh for whatever reason, BNBC 2020 does not refer to these headed stud reinforcement, which is basically indispensable in the design of flat plate column structures. Okay, we go to pre-stressing steel. It can be wire, A421, low relaxation wire, 421 with a supplement, strand, that means a number of wires wound together, A416, or it can be high strength bar, A722. Wire, strands, and bars not specifically listed in A421, A416, A722 are allowed, provided they conform to minimum requirements of these specifications and do not have properties that make them less satisfactory than those listed in those specs. Okay, then beyond reinforcing steel and pre-stressing steel, there are times when we use structural steel in concrete, steel pipes, or tubing. And there are specifications given. I don't think I need to or want to take time over those. Those are not common applications, but there are times when you do use structural steel pipe and tubing in concrete. If you do, there are ASTM specs governing their use. Continuing with structural steel pipe or tubing, then this is continuing. Again, I don't think that I want to spend time on those items. You can look them up. I do want to spend time, a minute or so, as I did on the headed stud shear reinforcement. This is, the color indicates to you that this is in ACI 31808, not in BNBC 2020. Steel discontinuous fiber reinforcement for concrete. Okay, this is recognized in ACI 318 as shear reinforcement under very tight controls. So this is an increasingly important item, in my opinion, that you should be aware of. The steel discontinuous fiber reinforcement. Other types of fibers like carbon fibers are not recognized by 318. And then headed deformed bars. Okay? So normally, to anchor a bar, we hook the bar into the concrete. But if it is a lot of reinforcement, the hooks lead to congestion, major congestion. So instead of using hooks, it is of great advantage many times to use heads. Those heads can be screwed onto the bars as shown in the picture, or they can be, the bars can be manufactured with the heads already welded to them. Okay? Both ways, these are headed bars. The headed bars are becoming more and more common, and they definitely are recognized in ACI 318. Headed bars, with headed bars, the development length requirement goes down because stresses are transferred not only by bond between the bars and the concrete, but also by bearing of the heads. The bearing of the heads on the concrete transfer a part of the stress that needs to be transferred between the reinforcement and the concrete. Okay? So those are two important items that you do not find in BNBC 2020, the steel discontinuous fiber reinforcement and the headed deformed bars. Okay, that brings us to admixtures for concrete, admixtures for water reduction, and setting time modification. Shall conform to C494, very important ASTM specs. Admixtures for use in producing flowing concrete. That is self-consolidating concrete. You don't have to vibrate. Shall conform to ASTM C1017. That is becoming a major subject in itself these days, the self-consolidating concrete. There's a lot of development, obviously, not within our scope today, but very interesting field that has emerged. Air and training admixtures, the spec is C260. Admixtures to be used in concrete shall be subject to prior approval. This ACI doesn't require this, but BNBC does. Admixtures to be used in concrete shall be subject to prior approval by the building official and conform to following standards. So BDS EN 934-1 or BDS EN 934-2. Fly ash or other pozzolans that will not be called admixture today. It's mineral admixture now, supplemental cementitious material. You have already seen the spec is C618, ground granulated blast furnace slag that is also cementitious material. ASTM C989, pigment for colored concrete, C979. BNBC cites those under admixtures for concrete. Calcium chloride for admixtures containing chloride from sources other than impurities in admixture ingredients shall not be used in pre-stressed concrete, in concrete containing embedded aluminum, or in concrete cast against stay-in-place galvanized steel forms. This is extremely, extremely important. Wherever you have potential corrosion, where any situation where you absolutely need to make sure that there will be no corrosion problem, you have to avoid calcium chloride in your admixtures. Okay, no calcium chloride in admixtures. So the 494, the admixture spec that tells you the types of admixtures that are pretty commonly used. Water reducing admixtures, 494 type A. Retarding admixture, this is set retarding admixture type B. Set accelerating admixture type C. Water reducing and retarding type D. Water reducing and accelerating type E. Water reducing high range admixtures F. Water reducing high range retarding admixtures. High range means it gets close to the what was it called, the self-consolidating. There was a flowing, so it gives you kind of flowing concrete. Okay, so water reducing high range admixtures, water reducing high range retarding admixtures, and then specific performance admixtures. A, B, C, D, E, F, G, and S, various types of A 494 admixtures used. BNBC cites BDS EN 934-1. Those are admixtures for concrete, mortar, and grout. Part 1 is common requirements. 934-2, admixtures for concrete, mortar, and grout. Part 2 talks about concrete admixture definitions, requirements, conformity, marking, and labeling. Storage of materials. Cementitious materials and aggregates shall be stored in such manner as to prevent deterioration or intrusion of foreign matter. Storage is extremely important. Prevent deterioration and intrusion of foreign matter. These things, when you read, doesn't read like much, but these are very, very important requirements. Okay. Durability requirements. Again, extremely important. Durability is like longevity in people. How long is your concrete going to last? How long is your concrete going to be serviceable, going to provide you, going to serve your purpose for which the concrete was installed? Okay. So for concrete intended to have low permeability, so-called watertight concrete. For concrete intended to have low permeability when exposed to water, the water cement ratio shall not exceed 0.5. Okay. So when we talk about durability, the various aspects of it are, there are typically four. Freeze thaw resistance, which is kind of moot in Bangladesh. So you have three considerations. One is resistance to sulfate attack. Second is this water tightness, permeability, however you want to describe it. And the third is corrosion protection. So sulfate resistance, corrosion protection, and permeability or lack of it, impermeability. Those are the three considerations. So BNBC starting with watertight concrete, intended to have low permeability when exposed to water. And what you need to do is to keep water cement ratio. It says today it would be water cementitious materials ratio. I think that's the way you should practice it, because that's what makes more sense. Shall not exceed 0.5. That is a pretty generous number. It is not a very tight restriction. So that's watertight concrete. For corrosion protection of reinforced concrete exposed to brackish water, that means water that stands still, seawater, or spray from these sources, spray from brackish water or seawater, the water cement ratio shall not exceed 0.4. Now it is much tighter. Okay, so for corrosion protection is a much tighter limitation on water cement ratio. If minimum concrete cover required by section such and such is increased by half an inch, so the required cover is 3/4 of an inch, you provide an inch and a quarter, water cement ratio may be increased from 0.4 to 0.45. Okay, so that can be relaxed. The 0.4 can be relaxed to 0.45 if you are prepared to use a thick cover. Okay. BNBC has this table of suggested workability of concrete for various placing conditions. Concreting of thin sections with vibration, degree of workability is very low. You need only very low workability. If it is concreting of heavily reinforced sections without vibration, you need very high workability. You need basically flowing concrete. Okay. And these values of workability, I wouldn't go into that. I don't even know about those things. Okay, so anyway, this is not common. This is not definitely in US codes and standards, but BNBC gives you this table of suggested workability of concrete for various placing conditions. I think it's a useful table. Okay, we talked about water tightness, we talked about corrosion resistance, now sulfate resistance. So this is a BNBC table. The number is 652, requirements for normal weight aggregate concrete exposed to sulfate containing solutions. Okay. If the sulfate exposure is negligible, then there is no limitation on maximum water cement ratio. If the sulfate exposure is moderate, then the limitation is 0.5. If it is severe, it's 0.45. If it's very severe, it's 0.45. How do you define negligible sulfate exposure as opposed to severe sulfate exposure in terms of water soluble sulfate in soil? This is percent by weight, and in terms of sulfate in water. Okay, so water soluble sulfate in soil and sulfate in water. And how you measure them is specified. There are ASHTO tests that you use. Anyway, this level of detail will not register. The important thing is that you have this table that tells you to go for tighter and tighter restriction on water cement ratio as you have more and more exposure to sulfate attack. And it is not only the limitation on water cement ratio, your cement has to may have to change, although here even for severe exposure, all you are being told you is you cannot use the Chem 1 cement. You have to go for Chem 2, and you cannot use blended type B. Okay, so it basically tells you that you have to go to Chem 2 cement, moderate sulfate resistant, rather than Chem 1. Okay, corrosion resistance, again, the topic came up, but this is further on that. For corrosion protection, maximum water soluble. So previously we told you that the water cement ratio has to be limited, okay, to whatever value. Now we are going further, and this is extremely important. For corrosion protection, maximum water-soluble chloride ion concentrations in hardened concrete at ages from 28 to 42 days, contributed from the ingredients including water, aggregates, cementitious materials, and admixtures, shall not exceed the limits given. That is a table. So if you have a corrosion problem, the chlorides from all sources have to be limited to values given in the table. This is extremely, extremely important for Bangladesh. There is a corrosion problem in most of the country, particularly in coastal areas. Chlorides cause the corrosion. The chlorides from all sources have to be limited, severely limited. When testing is performed to determine water-soluble chloride ion content, test procedure shall conform to the ASHTO T260 that I had in mind when I was talking a minute ago. When reinforced concrete will be exposed to brackish water, seawater, or spray from these sources. Requirements of section 5511 and 5512, those are the first two things that I showed you for water cement ratio or concrete strength. And so if your concrete is going to be exposed to brackish water, seawater, or spray from these sources, there is a limitation on water cement ratio that we went over. You can go back. I am not going to spend the time. And there is also a minimum cover requirement in section 818, chapter 8, which we will come to. Okay, so there is a comment. So both are required: the limitation on water cement ratio and adequate cover on reinforcement. So the maximum chloride ion content, as I said, there is a table giving you that. This is that table. This gives you the maximum chloride ion content depending upon your application. The minimum concrete strength that I mentioned, minimum concrete strength for structural use of reinforced concrete. This is not particularly for corrosion protection. This is across the board. Minimum concrete strength for structural use of reinforced concrete in BNBC is 20 megapascal, Newton per square millimeter, 20. However, for 20 is about 3000 psi. However, for buildings up to 4-story, the minimum concrete strength may be relaxed to 17 megapascal. 17 would be about 2500 or so. Okay, so those are very minimum concrete strengths. In IBC, it is 2500 psi across the board. We don't go up to the 3000 except in some cases. Corrosive environments. Okay, this is important stuff for Bangladesh. This is why I kept it here. The cover that was being referenced from earlier. Okay, if a thickness of cover for corrosive environment or other severe exposure conditions greater than the concrete cover specified in section such and such is required, such greater thickness shall be specified. So there are standard cover requirements in 8171 to 8176. But if thickness of cover for corrosive environments or other severe exposure conditions greater than that is required, then such greater thickness shall be specified. For corrosion protection, a specified concrete cover for reinforcement not less than 50 millimeters for walls and slabs and not less than 65 millimeters for other members may be used. For okay, the details you can read up, but for corrosive environments, the message is you may have to use the standard cover requirements. And the minimum compressive strength of concrete for corrosive environments or other, so it goes up to 25 MPa, and minimum cement of 400 kilograms per cubic meter. This is all important stuff for Bangladesh. Corrosive environment, your cover requirement goes up, minimum concrete strength goes up from 20 to 25 MPa, and minimum cement content kicks in 400 kilogram per cubic meter. Coarse aggregate shall be 20 millimeter down. I will let you read the rest of it because all the details will not register, but it is extremely important that you have these requirements on the books, and following them is in your interest. Use of brick chips as coarse aggregate is strictly prohibited for corrosive environment or other severe exposure conditions. Water cement ratio shall be 0.4 to 0.45. Potable water, drinkable water shall be used for all concreting. That exception goes away in corrosive environments. Okay, concrete quality, mixing and placing. I think I'm beginning to run late, so some of this stuff probably. Anyway, concrete shall be proportioned to provide an average compressive strength. So if specified compressive strength is 20 MPa, whatever, you have to set a required strength that is higher than that. And that would be F sub C R prime, R for required. Concrete shall be produced to minimize the frequency of strength tests below F sub C prime. F sub C prime is the specified value. So you will set a target value for proportioning that is higher F sub C R prime. And the idea is that concrete shall be produced to minimize the frequency of strength tests below F sub C prime. For concrete designed and constructed in accordance with the code, F sub C prime shall not be less than 17 MPa, which we have seen before. The requirements for F sub C prime shall be based on tests of cylinders made and tested as prescribed. So there is a section that tells you about the cylinder size and so forth. Unless otherwise specified, F sub C prime shall be based on 28-day tests. If other than 28 days, test stage for F sub C prime shall be as indicated in design drawings or specifications. That is a choice that the engineer has. But if you want strength at 42 days rather than 28 days, that has to be on your drawings or specs. So the only thing that is in BNBC carried over from 318 is splitting tensile strength tests shall not be used as the basis for field acceptance of concrete. It has to be compressive strength, not the split tensile strength. So proportions of materials per concrete shall be established to provide workability and consistency to permit concrete to be worked readily into forms and around reinforcement under conditions of placement to be employed without segregation and bleeding. Meet requirements for applicable exposure categories of chapter 4. So those are the durability requirements that have to be. So you have to comply with strength requirement, you have to comply with durability requirement, but you have to think of workability. The concrete has to be able to go where it needs to go. So that is extremely important. Workability, the durability considerations, and the strength. All three are important in proportioning. Where different materials are to be used for different portions of proposed work, each combination shall be evaluated. Concrete proportions shall be established. So you can proportion concrete on the basis of field experience or trial mixtures or both, or you can proportion concrete without field experience or trial mixtures and shall meet the applicable requirements. Okay, so all of this stuff now has been deleted from ACI 318, but it used to be older editions and they are in BNBC 2020. We have deleted them from 318 because the engineer does not typically deal with proportioning. It is done at the ready-mix concrete plant. So we have stripped ACI 318 of all this stuff. Proportioning on the basis of field experience and or trial mixtures, proportioning by water cement ratio when you don't have the basis field experience or trial mixtures. If you proportion by water cement ratio, then there is strength reduction that is specified. So all those details are in BNBC 2020. Evaluation acceptance, here we talk about testing, frequency of testing, lab cure specimens, field cure specimens, investigation of low strength test results. Steel fiber reinforced concrete is in ACI 31808, not in BNBC 2020. So I will not talk about these. And then there is a major there are major requirements concerning construction aspects, which are, again, I will not talk about them because there is time limitation, but everything about concrete, if you want the right product, if you want a properly constructed concrete structure, all of these items here are important. The mixing of the concrete, not just the proportioning, the mixing, the conveying. Okay, so typically these days a truck mixer comes from the concrete plant. It arrives at the job site. Then the conveying is typically through pumps in the United States. And then depositing, how do you put it in place from the head of the pump to where the concrete ultimately belongs? And then after you have placed the concrete, curing is absolutely terrible. Like there is nothing more important than curing of the concrete. You cannot let the concrete dry too quickly. That will lead to cracking and weaknesses. So these are all major topics that I do not have time to discuss, but please make sure that you understand them to be important and to follow not only the requirements in the code but also sound practice. Formwork embedments and construction joints, there are requirements given. This again should be taken seriously. Design of formwork, removal of forms, shores, reshoring. Shores are the posts and things that support the forms, Reshoring is you remove the forms when concrete has gained sufficient strength, but at that point you still have to keep the slabs supported. So you remove the shores to remove the formwork, but then you reshore. You put the post back, supporting the slab directly. Embedments in concrete, construction joints. Okay, so that brings me to I probably, yeah, I don't have a very good sense of the time that either segment to take, because I haven't done this before. Uh, so I have an hour and 10 minutes. It should be sufficient, I would think. Okay. So this is now the strength design method. Two design philosophies have long been prevalent: allowable stress design and strength design. The strength design, as we call it today, initially was called ultimate strength design, and the word ultimate eventually dropped out. I don't remember from what point onwards we have called it just strength design. So ASD, or allowable stress design, and strength design, two philosophies. Allowable stress design was the principal method used from the early 1900s. That's where we started, until the early 1960s. Okay. So even somebody of my vintage, we have really not done ASD of concrete. Allowable stress design of other materials. Steel was the next one to abandon allowable stress design. I won't be able to tell you the exact year, but it was like in the 80s in the United States. Masonry is in the process of switching now. Masonry 5 years ago was mostly allowable stress design. Some were switching to strength design. Today, I think it is 80-85% strength design, the remaining ASD. Wood is the material where ASD is still common. And wood is a very important material here in the United States. Anyway, so ASD was the principal method until early 60s. 31856, this is quite some time ago, was the first standard to officially recognize and permit the use of strength design. Okay, so 56. Starting from the 63 edition, there was a rapid transition to strength design, largely because of its rational approach and provision of better safety and reliability at the strength limit state. 1863 treated both ASD and strength design on an equal basis. So 56, strength design was introduced in an appendix. 63, both ASD and strength design were in the main body of the code. Large portions of ASD dealing with bond, shear, diagonal tension, combined axial load, and bending were modified to reflect behavior at nominal strength. By 31863, and then there was 31871. It remained the same as 31863, but by 31877, the allowable stress design was moved to an appendix. Okay, so strength design came in an appendix, was introduced in an appendix in 56. 63 and 71 both remain side by side in the main body of the code. 77 ASD now went to an appendix, and in 31802 it was gone. The appendix with ASD was deleted from 380. Okay. That is the brief history. So from 31802 onwards, we simply do not have allowable stress design of concrete. Strength design philosophy is very simply required strength. Required strength. The notation is always U must be less than or equal to design strength, or we must provide design strength at least equal to or in excess of the required strength. What is required strength? So there are service loads. Let's start there. Service loads are the loads specified by the building code which a structure is expected to support under normal usage. Okay? There are service loads and there are abnormal loads. We are talking about service loads specified by the building code which a structure is expected to support under normal usage. So service loads, so many pounds per square foot of live load, that would be a service load. We go from service load to service load effect. Okay? We have a structure. If you have a structure, there are dead loads already acting, the weights of the structural members, and then let us say we have live loads acting on the slabs. Now we analyze the structure elastically, and that gives us bending moments, shear forces, axial forces in the various structural members. These are internal forces caused by the external loads. Every word I'm saying is important. Please listen very carefully. So the service loads are imposed on the structure. We analyze our structure elastically under the service loads. We calculate bending moments, shear forces, axial forces in our structural members. Those are internal forces caused by the external loads. Those are also called load effects. Okay, so there are loads and load effects. The externally applied loads and the internal forces caused by the externally applied loads. The load effects are amplified by load factors to account for probable variations in service loads. Load factors are one or larger typically, although there are exceptions these days. Anyway, so service loads, load effects, we amplify the load effects by load factors because service loads may be exceeded. And then the factored service load effects are combined. Okay, so dead loads cause so much bending moment. Live loads cause so much bending moment at the same section of the same structural member. Wind loads cause so much bending moment at the same section of the same structural member. We factored the dead load moments by one factor. We have factored dead load moments. Then we have factored live load moments. The live load factor is different from the dead load factor. Then we have factored wind load moments. Wind load factor again is different, but these factored load effects are combined, and that gives us the required strength. Okay, so at a particular section, the factored dead load effects are 50 foot kips. The factored live load effects are 20 foot kips, and the factored wind load effects are 25 foot kips. So we have required strength of 50 plus 20, 70 plus 25, 95 foot kips. That is our required strength. We have to provide design strength in excess of that or at least equal to that. That is strength design. Okay. Now, what is this design strength? Okay, before design strength, the factor loads that I was talking about are also called strength level loads, the maximum load that any structure is designed to support. Load factors scale the effects of the service loads on a structural member up to the effects of strength level loads. I think this is all pretty understandable. Okay, service loads and strength level loads. When we apply load factors to the effects of service loads, we bring them up to the effects of strength level loads. Okay, what is design strength? Design strength comes from nominal strength, strength of a member or a cross section calculated using the assumptions and strength design provisions of ACI 318. Now, nominal strength also means we consider the nominal member dimensions. If we have designed a 15-inch by 20-inch member, nominal moment strength will be calculated based on the 15 by 20 inch section. We ignore the fact that in reality, the section is 14.5 inches by 20.3 inches. Okay, so we stick with the nominal dimensions, the nominal reinforcement, so many bars of so many millimeter diameter. So nominal strength is the strength for the section we have designed, calculated using the assumptions and strength design provisions of ACI 318. That nominal strength is discounted by a strength reduction factor phi. The notation for nominal strength, if it is bending strength, is M sub n for nominal. Phi times M sub n would be design moment strength. Okay, so the design strength is a strength reduction factor times nominal strength. Both nominal strengths and phi factors for reinforced concrete members are to be determined in accordance with BNBC 2020 or 31808. So the required strength is always sub U. This notation is extremely important. You have to stick with those. Required strength is very different from design strength. Required strength is the demand, design strength is the supply. The demand side is sub U, required, factored axial force, required strength P sub U, required shear strength V sub U, required moment strength M sub U, required torsional strength T sub U. The supply, nominal strength times P. The nominal strength is sub N. If it is axial load, P sub N. If it is shear, V sub N. If it's moment, M sub N, so forth. Design strength is P times P sub N, phi times V sub N, phi times M sub N. Okay. Why do we apply load factors? Probable variation in specific service loads because of variation in member sizes, variation in material densities, structural and non-structural alterations, degree of accuracy in load determination. Also, uncertainties in calculation of load effects on a member. So we go from load to load effects by analysis. In that analysis, we have to make assumptions of stiffness, span length, etc. Other assumptions and simplifications in the structural model used for analysis. There are uncertainties involved in all of those. We assume a particular stiffness may be different. This is why we need these load factors. Strength reduction factors. Why do we discount the nominal strength? Probable variation in material strength because of quality control, effect of testing speed. This is I don't know how many of you realize if you test something at a high speed, you will get higher strength than if you test the same thing under lower speed. Okay, so effect of testing speed, difference between in situ strength in-place strength and specimen strength. So we test cylinders. That is representative of in situ strength, but it is not exactly the same. Stresses due to creep and shrinkage. Probable variation in member sizes because of tolerances in formwork. Rolling and fabrication tolerances allowed for reinforcing bars. Tolerances in reinforcement placement. Strength reduction factor also accounts for various design assumptions and simplifications that cause the design behavior of structural members to deviate from the actual behavior, and finally, consequences of failure. When a column fails, it is catastrophe. When a beam fails, it may not be a big deal. Beams can be much more easily repaired than columns can be. So columns have to be assigned a significantly lower phi factor than beams. Okay, consequences of failure. Okay, so that up to that is a basic strength design that we have had since 63. From 56 to 63, significant changes were made in strength design, but from 63 onwards, details have changed, but we stayed with the same strength design basically. But then came unified design provisions in relatively recent times, 3/1895. A modified version of the strength design method was first introduced in 3/1895. And the whole idea was consistent design provisions for reinforced and pre-stressed concrete beams and columns. Prior to the introduction of unified design, there were differences, material differences between how we treated beams versus columns and how we treated pre-stressed concrete versus conventionally reinforced concrete. Ideally, there should not be any difference between a beam and a column. A column is subject to axial load and bending moment. In the case of a beam, the axial load has become zero or very negligible. It is all bending moment. But there is no fundamental difference between the members. Also, pre-stressed concrete and reinforced concrete should be viewed as two extremes of a continuum, which is partially pre-stressed concrete. You can combine reinforcing steel and pre-stressing steel in the same member, and depending upon how much of the load effect is resisted by the pre-stressing steel versus reinforcing steel, you can have behavior approaching that of a reinforced concrete member to behavior approaching that of a pre-stressed concrete member. So it should be a continuum. There should not be any fundamental difference in the way we treat reinforced concrete members versus pre-stressed concrete members. That was the idea behind unified design. Okay, so under this unified design introduced in 3/1895, the phi factor became a function of the so-called net tensile strain, a very important term now, epsilon sub t, net tensile strain. So phi is now a function of the net tensile strain epsilon sub t. Net tensile strain is the tensile strain at nominal strength, exclusive of strains due to pre-stress, creep, shrinkage, etc. Okay. Let me do it this way. Nominal strength. something very, very fundamental to ACI 318 from the beginning of strength design has been that a section attains its nominal strength when the extreme compression fiber concrete strain reaches a value of 0.003. I will repeat. Every bit of what I'm saying now is extremely important for you to understand. ACI 318 has only one definition of nominal strength. A section is considered to have attained its nominal strength when the extreme compression fiber concrete strain reaches a value of 0.003. Net tensile strain is the strain in the tension reinforcement when that happens, when the concrete strain at the extreme compression fiber reaches a value of 0.003. Okay. And we call it net tensile strain because the strain in the reinforcement must be caused entirely by externally applied loads. We shall not include any strain caused by pre-stressing or creep or shrinkage or things like that. Okay, so net tensile strain is the strain in the tensile reinforcement corresponding to a strain of 0.003 in the extreme compression fiber of the concrete. Now, when I said strain in the reinforcing steel, it is actually strain in the extreme tension steel. What is extreme tension steel? The reinforcement that is the farthest from the extreme compression fiber. Very simple. Okay. So net tensile strain is the strain in the extreme tension steel corresponding to a strain of 0.003 in the extreme compression fiber of the concrete. Okay. So there are two layers of reinforcement. This is the extreme tension steel, farthest from the compression face. When the strain in the concrete is 0.003, what is the strain in the extreme compression, in the extreme tension steel? That is epsilon sub T, as clearly shown in the picture, net tensile strain. And the word net again implies that we must not include in epsilon sub T any effect of pre-stress or creep or shrinkage or things like that. All of epsilon sub T shall have been caused by externally applied loads. Why? So this unified design that is in ACI 318 was the contribution, let me say, of Bob Mast, Robert Mast, who was truly an outstanding engineer. He died relatively recently at the, he lived to his late 90s and was very sharp until the end. One of the smartest engineers that has been my privilege to know. Bob Mast went for net tensile strain as the basis of his unified design because it is indicative of both excessive cracking and excessive deflection. Let me go one step back. Concrete, a properly designed concrete member should give you warning of failure. It should not fail all of a sudden. This is why we limit the amount of tension reinforcement in a concrete member to have warning of failure. The warning comes in the form of cracking and deflection. Cracking and deflection. Both are related. When concrete deflects, it cracks, and when it cracks, the cracking causes the deflection. The net tensile strain is indicative of both excessive cracking and excessive deflection. This is why he thought it was a suitable quantity to anchor the whole thing on. Now, in these unified design provisions, we talk about, we have net tensile strain, and then we talk about compression controlled strain limit, the net tensile strain at balanced strain condition. Okay, so balanced strain condition means the reinforcement yields at precisely the same moment that concrete compression fiber reaches a strain of 003. So the compression control strain limit is basically the yield strain of the reinforcement. Okay? Compression control strain limit is the net tensile strain at balanced strain conditions. Balanced strain conditions mean the steel, the extreme tension steel yields at the same instance that the extreme compression fiber reaches a strain of 003. Then we talk about compression control and tension control sections. Okay, so we have talked about net tensile strain. We have talked about compression controlled strain limit. Now we are talking about compression control section, and next you will see tension control section. Compression control sections are, no, sections are compression controlled if the net tensile strain as defined is equal to or less than the compression controlled strain limit. Okay, if the net tensile strain is equal to or less than the compression control strain limit. For grade 420 reinforcement, that's grade 60 in our case, and for all pre-stressed reinforcement, very importantly, it shall be permitted to set the compression control strain limit equal to 002, the yield strength of grade 60 reinforcement. Okay? So when we talk about compression control strain limit, that limit is typically 002 if we are dealing with grade 60 reinforcement. That is changing now these days, but for all practical purposes, in most applications, the compression control strain limit is 002, and a compression control section is a section where epsilon sub t, the net tensile strain, is less than or equal to 002. Tension controlled section. Sections are tension controlled if the net tensile strain is equal to or larger than 005. Okay, 002 and less is compression controlled, 005 or more is tension controlled. Epsilon sub t is greater than or equal to 005. So there are compression control sections, tension control sections, then there are transition sections. Compression control sections, net tensile strain 002 or less. Tension control sections, net tensile strain 005 or more. Transition sections are sections where epsilon sub t is between 002 and 005, as simple as that. Okay. So in picture, you see epsilon sub t just defined just as before, the strain in the extreme tension reinforcement corresponding to a strain of 003 in the extreme compression fiber of the concrete. If epsilon sub t is less than or equal to 002, we have a compression control section. If epsilon sub t is larger than or equal to 005, we have a tension control section. In between, we have a transition section. Okay, now the phi factors. Tension control sections, phi is 0.9. Notice we don't say phi of 0.9 for flexure or for beams. It is for tension control sections, 0.9. If it is a compression control section, spirally reinforced member, 0.75. If it is not spirally reinforced, the phi is 0.65. Notice again, we don't say phi of 0.75 for columns. Okay, it's compression control sections that are spirally reinforced. In this text is better shown by this picture. So for tension control sections, epsilon sub t of 005 or more, phi is 0.9. For compression control sections, epsilon sub t of 002 or less, phi is 0.65 or 0.75. In between, for transition sections, we go on a straight line. Phi is interpolated linearly between the lower value and the higher value, 6.5 and 0.9 or 0.75 and 0.9, as simple as that. Linear interpolation between the lower value and the higher value. Next is something that is in BNBC, not in SEI 318. It shall be permitted for compression control sections, the following optional, more conservative alternative values of strength reduction factor phi, where less controlled construction environment justifies such selection according to engineering judgment of the designer. Spirally reinforced, you use 0.7 instead of 0.75, and non-spirally reinforced 0.6 rather than 0.65. I think this is an unnecessary provision because you can always go lower than the code. As I emphasized, I think the very first time we met, okay, code sets minimum requirements. You can always go above the code. So when the code says P of 0.75, you can always use a lower P factor as the designer. Okay, the code doesn't have to give you specific permission. So why this lower phi value for compression control sections? Compression control sections, such as columns, are assigned lower phi factors than tension control sections such as beams because compression control sections generally have less ductility. Ductility is the ability to keep on carrying loads as you deform. Compression control sections are more sensitive to variation in concrete strength. That is absolutely true. A beam is governed in its behavior by the reinforcing steel. The concrete hardly plays a role. As the compression increases, the concrete plays more and more of a role. So compression control sections are more sensitive to variation in concrete strength. Generally, the consequences of column failure are more severe than those of a beam failure. I mean, nothing truer can be said. Column failure is a huge problem. Stability of a structure depends on the columns. Compression control sections in members with spiral reinforced are assigned a higher phi factor than those in members with tie reinforcement because members with spiral reinforcement have greater toughness and ductility. Those are all like the loads can be maintained as the member deforms. The toughness, ductility, all those terms convey the same meaning, more deformable. You can carry the same load while undergoing larger deformations. And this was amply demonstrated when one of the 9/11 planes hit the Pentagon in 2001. Okay, so Uh, Anyhow, you know this. The spirally reinforced column is more ductile, more deformable than a tight column, and this is why it deserves a higher phi factor. The other phi factors, shear and torsion 0.75, bearing on concrete, post-tension anchorage zones, stud and tie models, which, yeah, anyway. I it's approaching 10 o'clock, so I am not sure I want to go into this now. Uh, so this is P for pre-stress member. I will skip these two slides. If you have any interest, there is a question, I'll come back. I don't have any problem. This is just to conserve a little time. Okay, so safety margin is provided by a reduction in member strength by phi factor, increase in the imposed loads by the load factor. We have both. So safety margin is the load factor divided by the strength reduction factor. And then we say direct calculation like this is not always possible. Actually, it is seldom possible, but some of the time you can do that. So this is an example, design of a beam for flexural moment from dead load. That kind of a simple case, you can do this kind of figuring. So m sub u has to be less than or equal to phi times m sub n. M sub u is 1.4 times the bending moment caused by dead loads. AC7 tells you that, BNDC tells you that 1.4 is the load factor if only dead loads are acting on your structure. P is 0.9 for flexion. So the safety margin in this case is 1.4 divided by 0.9, which is 1.56. Load factors and strength reduction factors are provided after considering probability of actual imposed loads exceeding and member strengths falling short of the respective design values. So load factors and strength reduction factors are provided after considering probability of actual imposed loads exceeding and member strengths falling short of the respective design values and severity of failure if the above does happen. So in setting the safety margin, various items are considered. The type of failure, warning of failure, existence of alternative load paths, that's also very important. If something fails, are there alternative load paths available? Is there redundancy in the structure? Importance of structural element within the structure. Is it a beam or a column kind of thing? Potential loss of life, cost to society in lost time, lost revenue, or indirect loss of life or property due to failure. Cost of replacing the structure. All of these are considerations in setting the safety margin in our codes. There was pioneering work before we finalized the strength reduction factors, and the load factors come from AC7, but even then ACI 318 used to modify them. But before we settled on the strength design that you basically find in ACI 318, or has been in ACI 318 since let us say 1971 when it settled down, was based on pioneering work by Jim McGregor. And in this paper, he says something that I would like to throw in, and then probably it's better to move on. The ACI design requirements are based on an underlying assumption that if the probability of understrength members is roughly 1 in 100, understrength member, one member in 100, and the probability of overload is roughly 1 in 1,000. The probability of overload on an understrength member or structure is 1 in 100,000. Load factors were derived to achieve this probability of overload. So the load factors were based on this probability of overload, 1 in 1,000 members being overloaded. Based on the P factor, based on values of concrete and steel strength corresponding to a probability of understrength of 1 in 100, the strengths of a number of typical sections were computed. The ratio of the strength based on these values of the strength based on nominal strengths of a member of typical section. Anyway, I'm not doing the best job of reading. I would let you read it. So Jim McGregor in that pioneering paper gives you the basis for the load factors and the phi factors used in ACI 318. The load factors are basically adopted from ACE 7, which are also adopted by the IBC, International Building Code. You do not have multiple sources. You have the load combinations in BNBC, and I will go there. Okay, so a structural member is required to be designed for a number of, here it is coming. So a structural member is required to be designed for a number of combinations of these effects of various factored loads. Okay, remember, loads, load effects, factored load effects, and then combinations of factored load effects, which is our required strength. Okay, I'll do it again. We have service loads, service load effects, factored load effects, and then combinations of factored load effects, which is the required strength. Strength designed load combinations are provided. Notice I did not even mention ACI 318. In the US, because the load combinations are given in the IBC, those are the load combinations you must use in design. Those are based on ASC 7, but when a code and a standard cover the same topic, you go with the code, not the standard. Your case, that problem doesn't arise. Your load combinations are in BNBC 2020 section 2.7.3. You have one place to go. Yeah, here I'm telling you that the code governs, not the standard. Okay, so these are the design load combinations of 2009 IBC and BNBC 2020. Same load combinations. D is the effect of dead load. F is the effect of fluid pressure. T is typically called temperature effect, although that is a misnomer. That is actually, let me go there and come back. I think I had it. So D is dead load effect. F is fluid load effect. T is effect of self-straining forces. That's a much better way of saying. T stands for temperature, but it is the effect of restrained volume changes. That's what it is. Effects of restrained volume changes, T. L, live load effect. H, effect of lateral earth pressure, very important. L sub R, roof live load effect. R, rain load effect. W, wind load effect. E, earthquake effect. Okay, so F is fluid load effect. T is effect of restrained volume change. H, effect of lateral earth pressure, and so forth. So if it is only dead load acting on the structure plus the horizontal earth pressure, if present, then the load factor is 1.4. When it is dead load in combination with live load and roof live load or rain, the dead load factor is 1.2. Anyway, so this is dead load, this is dead plus other gravity loads, this is dead and rain and wind, this is dead. So these are load combinations involving wind. There are three of them: 3, 4, and 6. 3 and 4 are where the effects of gravity loads are additive to those of wind loads. 6 is where the effects of gravity counteract the effects of wind. There are two load combinations involving earthquake effects. This one, number 5 and number 7. 5 is additive, gravity effects add to earthquake effects. 9 is counteractive, gravity effects counteract earthquake effects. Okay, so these are we call them load combinations. They are actually combinations of load effects. That's very, very important. You cannot combine loads. Dead loads act vertically down. Live loads act vertically down. Wind loads act sideways. How do you combine? You cannot combine. We never have combined loads. Dead loads cause bending moments at the support section of a beam. Live loads also cause bending moments. Wind also cause bending moments. We combine the bending moments, the load effects. So we call them load combinations. They are combinations of load effects. The load factor on live load. So what we are saying is, in the load combinations, the live load factor here is 1.0. 1.0. Most of the time that 1.0 can be taken as 0.5, except in 3 cases. You have to take the live load factor as 1.0 for parking structure decks, for assembly areas, and for areas supporting more than 100 pounds per square foot of live load. 100 pounds per square foot in your case is 5 kilonewton per square meters. Okay, so unless you are designing a parking structure, a place of public assembly, or an area supporting more than 100 pounds per square foot of live loads, your live load factor is 0.5 rather than 1.0. The load factor on H. So in these load combinations where you have wind and the horizontal earth pressure, earthquake and the horizontal earth pressure, the load factor on H is 1.6 when it hurts, but it is 1.0 when it helps. If the bending moment caused by horizontal earth pressure is in the same direction as bending moment caused by wind or earthquake, the load factor on H is 1.6. However, if the overturning moment caused by horizontal earth pressure counteracts the overturning moment caused by wind or earthquake, the load factor on H is 1.0, not 1.6. Okay, that's very important. So that's said in exception 2. Exception 3 talks about directionality of wind, and I will come to that in just a second. Okay. Okay, directionality is coming right up. Earthquake loads computed in accordance with 2009 IBC or BNBC 2020 is already a strength level load. This is why the load factor on E, earthquake effect, is 1.0 in the load combinations. Okay, if you noticed, load factor on W, wind, is 1.6, load factor on E is 1.0. The load factor on E is 1.0 because E is already at a strength level. Okay, this is BNBC, not ACI 318. When a structure is located in a flood zone or in tidal surge zone, the following load combination shall be considered. In coastal zones vulnerable to tidal surges, 1.6 W that you saw in that load combinations shall be replaced by 1.6 W plus 2.0 F sub A, where F sub A is the effect of flood load. That has to be calculated according to BNBC 2020. Okay? So in coastal zones vulnerable to tidal surges, 1.6 W shall be replaced by 1.6 W plus 2.0 F sub A. In non-coastal zones, 1.6 W shall be replaced by 0.8 W plus 1.0 F sub A. These are BNBC provisions that are important for you to keep in mind. For many members, the only loads considered are dead, live, wind, and earthquake. The FHRST go away, and then the load combinations get reduced to what you see in this picture. The F sub 1, F sub 2 are not F sub 2. The F sub 1 load factor on the live load is an IBC creation. F sub 1 can be 0.5 or 1.0. As I mentioned, it is 0.5 unless you are designing a parking structure, a place of assembly, a place of public assembly, or an area supporting more than 100 pounds per square foot of live load. Yeah, so in addition to the possible variability of the specified loads, values of load factors are also assigned based on the probability of simultaneous occurrence of different load types. For example, the load factor on dead load alone is 1.4. Alone, the load factor on dead load alone, which is 1.4, is higher than the load factor on dead load 1.2 when other loads such as live load, wind, etc. are also present. Okay, now let us talk about the directionality of wind. You have seen that the wind load factor is 1.6. It used to be 1.3 earlier. It has changed from 1.6 now. That's in the, for you, that's in the future. But for you, 1.6 in BNBC 2020, that 1.6 at one point used to be 1.3. Now, this will be the subject in one of our seminars after we are done with concrete when I talk about wind. This is the so-called velocity pressure due to wind, and that has a directionality factor K sub D in it. This K sub D accounts for the fact that wind seldom, if ever, is along the most critical direction of your building, because wind direction changes from one instant to the next. One instant it may be along the most critical direction, but the next instant the wind direction will have changed and it will no longer be along the most critical direction. This fact is taken into account through a directionality factor, which is 0.85 for all buildings. Now, this directionality factor used to be included, or this directionality thing used to be included in the load factor of 1.3 when it was 1.3. The load factor of 1.3 was deliberately chosen low because it included directionality of wind. But at one point, ASC7 decided to introduce a separate directionality factor K sub D, 0.85 as I mentioned for all buildings. So now the load factor of 1.3 the directionality factor had to be taken out of the load factor. So the new load factor became 1.3 divided by the directionality factor of 0.85. Are you following me? 1.3 included a directionality factor of 0.85. But at one point in ASC 7, 1998, ASCE introduced a separate directionality factor K sub D in the expression for wind pressure. So now the wind load factor had to be decreased by the same directionality factor. The new load factor needed to be 1.3 divided by 0.85. That gives you 1.53. The 1.53, instead of being rounded down to 1.3, was rounded up to 1.6. So that's the history beyond 1.6. And that brings us to exception number 3, which I skipped. So exception 3 says, for structures designed in accordance with the provisions of such and such, where wind load has not been reduced by a directionality factor, it shall be permitted to use 1.3 W in place of 1.6 W. If wind does not include directionality, your wind load factor should be 1.3. If wind includes directionality, which it normally would, if you calculate wind by BNBC 2020, then the proper load factor on wind is 1.6. Okay. Now the seismic load combinations, additive, 1.2 dead, 1.0 live, which would typically be 0.5 live plus 1.0 E, and the counteractive 0.9 dead plus 1.0 E. Okay. Now let me do it slightly differently than how the slides are. Let me do it what is in the IBC, and then I'll take you back to BNBC. Okay. So in seismic design, we start with the design base shear V, and we will do this. There are seismic modules coming up. We distribute the V along the height of the structure in the manner prescribed by the code. That gives us lateral forces at the various floor levels. We analyze our structure elastically under those floor level forces. The IBC notation for which is capital F sub X, X for floor level X. This analysis will give us bending moments, shear forces, axial forces at the various critical sections of various structural members. The generic notation for those internal forces in the IBC is Q sub E. That's bending moment at a beam section caused by the earthquake forces. The horizontal earthquake forces, let us say. Q sub E is also shear at a beam section caused by the horizontal earthquake forces. And Q sub E is also axial force in a column section caused by the horizontal earthquake forces. Now, in the additive seismic load combination, 1.2 dead, 0.5 live, 1.0 E, the earthquake effect E is taken as the horizontal earthquake effect Q sub E amplified by a redundancy factor rho, and then Added to that is a vertical earthquake effect, which is taken as 0.2 S sub ds short period design spectral acceleration times the design dead load. Okay. So the earthquake effect E is the combination of horizontal earthquake effect and vertical earthquake effect. The horizontal earthquake effect is taken as the Q sub E, as I described earlier, multiplied by the redundancy factor rho, and the vertical earthquake effect is taken as 0.2 times S sub ds, which will be described in great detail in our seismic modules, times the design dead load. Now, when we collect terms, what we get is 1.2 plus 0.2 S sub ds times d plus rho times Q sub E plus 0.5 L. So what we have done is, in this additive seismic load combination, we have increased the dead load factor from 1.2 to 1.2 plus 0.2 S sub ds by considering vertically downward earthquake ground motion. If S sub ds is equal to 1, then the dead load factor is 1.4 instead of 1.2 in consideration of vertically downward earthquake effect. In the counteractive load combination, 0.9 dead, this is plus 1.0 E, we write, so make this, I should have made this change, write this plus. So in this load combination, the 1.0 E is taken as rho times Q sub E minus 0.2 S sub ds times D. Okay, we consider vertically upward earthquake ground motion. And then we get 0.9 minus 0.2 S sub ds as the dead load factor plus rho times Q sub E. Okay, so in the slide that will be posted, I'll change the signs, but read it this way. 0.9 dead plus 1.0 E. 1.0 E is rho times Q sub E minus 0.2 S sub ds times D in consideration of vertically upward earthquake effect. And that decreases the dead load factor from 0.9 to 0.7 when S sub ds is equal to 1. So when earthquake effects are additive to seismic effects, we consider vertically downward earthquake effect, thereby increasing the dead load factor. And when earthquake effects when dead loads counteract earthquake effects, we consider vertically upward earthquake effect, thereby decreasing the dead load factor. Okay. Now, for certain members, like columns supporting discontinued shear walls, we use so-called special seismic load combinations, or load combinations including overstrength factor, where instead of rho times Q sub E, we use omega sub 0 times Q sub E. The redundancy factor rho is 1 or 1.3. This omega sub 0, the so-called overstrength factor, is 2, 2.5, or 3. So in the design of particularly vulnerable members, like a column supporting discontinued shear walls, we use these load combinations with overstrength factor. B and BC exactly mirrors what is in the IBC, except that the vertical acceleration term is 0.5 times A sub H times D, and I'll explain that this is exactly equivalent to 0.2 S sub ds times D when I do my earthquake module with you. Okay, so what I described for the IBC is exactly the same in the BNBC. Earthquake effect is a combination of horizontal earthquake effect and vertical earthquake effect. The horizontal earthquake effect is rho times the effect of the code prescribed seismic forces, and the vertical earthquake effect is 0.2 S sub ds times D. Okay, now I'm definitely beginning to run late, but I don't have a lot more to cover. Okay, Unified Design Provisions first introduced in 31895, moved to the main body in 2002. Since then, this is the way to design concrete, the Unified Design Provisions. Okay, much of it, I uh, actually I meant to skip. I know that. Okay, so see, so the only remaining things that I want to cover with you, the slides that I'm skipping point out that prior to this is okay. So 31802 is when unified design came into the main body of ACI 318. The ACI 318 edition before that was 99, 31899. So in the slides that I'm skipping, I go back to ACI 31899 to tell you what the problems were, how we failed to treat reinforced concrete and pre-stressed concrete beams and columns the same way, which was in Bob Mass' mind the justification for unified design. Okay, so that's what I'm skipping. For you, 99 ACI 318 does not make any difference because your basis is 31808 much later. So I keep those slides in, but there are no consequences. Two things are important. One is this. So prior to switching to a unified design where we have tension control sections, epsilon sub t of 0.5, 0.005 or more, compression control sections, epsilon sub t of 002 or less, and transition sections. We used to have a maximum limit on tension reinforcement, which was 3/4 of rho balanced. Balanced reinforcement ratio is the reinforcement ratio that leads to yielding of the extreme tension reinforcement at precisely the same moment that the extreme compression fiber concrete gets to a strain of 003. Okay? So in a flexural member, in a member with phi times p sub n not exceeding 1/10 f sub c prime a sub g, or phi times. So let us say in a flexural member, that's what this describes. We could not place any more tension reinforcement than 3/4 of rho balanced. There was a pre-stressed concrete counterpart that I will not even get to. So keep that in mind. Now under unified, and there was, so the maximum tension reinforcement ratio was 3/4 of rho balanced, and there were provisions for moment redistribution, which were quite different between pre-stressed concrete and reinforced concrete. Unified design, we modified both, and this is what I'm coming to is what is of interest to you. Okay, this is what is in 31808, and this is what is in BNBC 2020. So we are now talking about redistribution of bending moments. Applies equally to both non-pre-stressed and pre-stressed sections. The moment redistribution now is based on net tensile strain, epsilon sub t. The percent redistribution that you are allowed is 1000 times epsilon sub t. does not matter, reinforced, pre-stressed, your moment, the moment redistribution that you are allowed to take is no more than 1000 epsilon sub t. And you cannot take any moment redistribution unless your epsilon sub t is at least 0075. Okay, that's what we say here. Maximum redistribution you can take, irrespective of the value of epsilon sub t, is 20%. So the redistribution you are allowed is 1000 epsilon sub t. You cannot take any redistribution unless epsilon sub t is at least 0075, and the maximum you can take is 20%. Okay. Now, moment redistribution now can be, you decrease the negative moment by delta m, in which case the positive moments will increase. But unlike in older times, we are also allowed to decrease the positive moment by the same delta sub m, in which case we'll end up with more negative moment. It depends on the situation you are facing. If you want to decrease the negative moment, you will take a redistribution on the negative moment. If you want to decrease the span moment, you will decrease the span moment and the negative moment will go up. Both are allowed. Moment redistribution may not be used for slab systems designed by the direct design method. There are two ways of designing the two-way slabs, direct design method and equivalent frame method. If you're using direct design method, then there is no moment redistribution. Okay, so now moment redistribution, this is net tensile strain has to be at least 0075. As soon as it is 0075, we can take 7.5% moment redistribution, 1000 times 0075. We can go up to 20% for a net tensile strain of 0.02, and it remains there. We cannot go any higher. This used to be SCI 31899 moment redistribution for reinforced as opposed to pre-stressed beams. For pre-stressed beams, now there is no difference. The moment redistribution is, as I described, 7.5% at 0075, going up to 20% at 02. But the moment redistribution of 31899 was as shown here. So that is moment redistribution. Now the maximum reinforcement. This is the last topic. Remember, we could not go beyond 3/4 of row balanced. Now we say for fractional members with P sub U, required axial load less than 1/10 F sub C prime A sub G, required axial strength less than 1/10 F sub C prime A sub G, net tensile strain shall not be any less than 004. Tension control sections start at 005. We are not saying all flexural members have to be tension controlled, but we are saying that the net tensile strain cannot be any less than 004. This is extremely, extremely important. This takes the place of rho maximum shall not exceed 3/4 of rho balanced. It replaces rho maximum less than or equal to 3/4 of rho balance that we used to require from the beginning of strength design. The new limit is slightly more restrictive. For rectangular sections, the new limit corresponds to 0.714 row balance rather than 75% of row balance for grade 420 reinforcement. Okay, and that's about as far as I need to go. Pre-stressed, I will not worry about. So it's not too bad. 10:30 was the target. It's 10:34 or so I have time for questions. So the first half was the material provisions. The second half, strength design, and then I went to the unified design that is currently in the code. starting with 31802. That definitely is what you have in BNBC 2020. And the last two things that I talked about, moment redistribution, I don't know, is terribly important because it is becoming increasingly uncommon to take moment redistribution, but the net tensile strain cannot be any less than 004 is vitally important in the strength design that we do these days. Now, starting with ACI 31819, we have said all beams shall be tension controlled, but for you that is in the future, and probably in the far future, so I will not go there. For a long time to come, your practice will have to be net tensile strain shall not be any lower than 004. Okay, thank you very much. I'm open to questions, and so Bodhi, you will read to me and I will try to answer. Is that the idea?
Yeah, I can do that, Dr. Ghosh.
Okay.
You can also access the question answer, do you should see the Q&A
Yeah,
option?
let me see. Yeah. Okay. Select.
And Dr. Akib is also there as co-host, so
Okay.
he can unmute
Great.
himself anytime
Great.
if he wants to answer
Maybe
or
he
if he
can
wants to ask
answer.
something.
Maybe he can answer all the questions. How is that? No,
That is also
I'll try.
possible.
No, let's. Yeah,
Yeah.
I'll go to him if I need. Yeah.
Okay.
Maybe read them. I don't know how to.
Okay. Uh, Select the elements like beam connected between column and shear wall. Do we need to design with seismic overstrength factor?
There's a beam between a shear wall and a column.
Right.
Do we need to? No, absolutely not. No, no overstrength factor. No, there are only three cases where the seismic overstrength factor is required to be used. I will go over those three cases in the proper seismic module, so please be patient. But let me mention one thing that is vitally important. Do not use the special seismic load combination when not specifically required to do so. Because in seismic design, more is not necessarily better. You cannot, let us say you have a structure with 36 columns in it. And for whatever reason, one of those columns becomes your favorite, and you decide to design it using the special seismic load combinations. So you make this column stronger than the other 35 columns. That will be detrimental to the structure. The strong column will draw more loads to itself. That will be the first one to fail. Then the loads carried by this column will have to be distributed to the other 35 columns. So you will be dealing with a much more difficult problem than you started with. So please do not use the special seismic load combinations when not specifically called upon to do so. And the only three cases where it is required to be used, I will go over very carefully in one of the seismic modules.
Okay, Dr. Woods. So why is the earthquake force increased by overstrength factor for columns supporting discontinued shear wall?
Column supporting discontinued shear wall, there is no more no more of a critical situation. Okay, so in a large part of the world, people park their cars underneath their apartment buildings. So the ground level is open, you have columns, and then above the parking level, the ground level, shear walls start. And these columns of the ground level support the stiffer structure above. This gives you what is typically referred to as soft story. Okay, so if an earthquake comes, the earthquake induced deformations will be concentrated in these columns, in this story consisting only of columns, and while the stiffer structure upstairs will remain basically elastic. And these columns will fail unless you do two things. You make them stronger by designing using the load combinations with overstrength. That is only one of the things you have to do. Second thing you have to do, and this I will also go over in great detail, you have to detail these columns, the entire height of these columns, in a very stringent manner. We have prescribed details that have to be applied to the entire height of these columns. So this is the most critical situation, the most critical structural member that an engineer typically has to design in an earthquake situation, a column supporting a discontinued shear wall. Okay, so okay, go ahead. Another question.
Uh, Please explain the difference between creep and shrinkage of concrete, and how does it affect the strength of concrete?
Difference between creep and shrinkage and how it affects
Affects.
strength
Yeah.
of concrete.
Yeah.
Okay, first of all, the difference between creep and shrinkage. Shrinkage is very simply water going out of the concrete. Okay. So remember, concrete is cement, sand, stone, and water. The cement binds because it chemically reacts with the water, creating a cement paste, and that paste binds together the sand and the stone. This cement paste, as it hardens, cement paste hardens with time, and the excess water that was not required for hydration of the cement escapes out of the concrete. This is why curing is so crucial. You cannot let the water evaporate quickly because that will cause problem. And I have only so much detail I can go into because of time limitations. Anyway, so shrinkage is the volume change. It's always a decrease in volume because of the water getting out of the concrete, the water that is not needed for hydration of the cement eventually escaping out of the concrete. Okay? Creep, on the other hand, is a load-dependent phenomenon. When you load a structural member, it suffers immediate elastic deformation. You put axial load on a column, it shortens immediately. But if you simply keep the load in place, that initial shortening will go on increasing with time. If you have a tenth of an inch shortening immediately upon load application, that tenth of an inch will become 3/10 of an inch in several years. Most of that increase of 2/10 of an inch, which is the increase, is called the creep, not the total. So immediate deflection or deformation, and then the time dependent increase make up the total long-term deformation. The increase in the immediate deformation is called the creep of concrete. Shrinkage is a load independent phenomenon. Creep is a load dependent phenomenon. both are deformations of the concrete. If compression is applied to concrete, the deformations caused by that compression will increase with time. Tension is a different thing. Tension will cause cracking and failure, so I'm not going there. Shrinkage will also cause a decrease in volume. And okay, now effect on strength, I don't know how to answer it. Let me say the most important thing. So neither creep nor shrinkage is a problem if you can let it happen. So you cast a 20-foot long concrete beam. It wants to shrink down to 19 foot 10 inches. If you let it shrink, nobody will miss the 2 inches, or very few will. That's not the problem. The problem is most of the time, basically all the time in cast-in-place concrete, this beam will be restrained. The beam will be framing into columns or walls which will not let this beam shrink. And when something wants to shrink and you don't let it shrink, that means you are stretching on it. You are stretching it. You are pulling on it. And that causes tension. And concrete is weak in tension. So now the beam cracks. So those are the problems with volume changes, whether it is due to creep or shrinkage. If you restrain volume changes, that causes problems that you have to contend with. So you either have to make allowances for this, or you have to deal with the consequences of the restrained volume changes. Okay, that would be my answer. I don't otherwise know how to say the effect of shrinkage on strength. I don't know that there is an effect. Okay. Next one, buddy. Buddy? Have I lost connection?
Dr. Harsh, I can hear you,
Oh, what happened?
but
What happened?
Bodhi, I don't know what happened to Bodhi.
Oh, sorry, I was muted.
Okay.
I was trying to read the question and I was saying that this is something that Dr. Rakib
Okay.
can answer. So the question is there any demerit of TMT rebar over homogeneous rebar for using in RCC if both types are of acceptable strength and ductility found from test?
This is for Dr. Rakib.
Okay. Um, uh, Basically, with the TMT rebar as compared to the homogeneous rebar, there is no severe problem or no problem during in terms of strength. If the strength is comparable in terms of strength and load carrying capacity, there shouldn't be much problem. But there is one problem with TMT repair, is that it is comparatively more susceptible to corrosion. Empirically, experimentally, it was found that TMT rebars are more susceptible to corrosion. So we have to keep that in mind, that in Bangladesh, most of the higher strength rebars like 500 grade rebars are TMT rebars, and they are comparatively more susceptible to corrosion than homogeneous rebars. That is one thing that we have to keep in mind. Other than that, other performance are similar. Thank you.
Thanks a lot.
Thank you, Dr. Rakib. So the next is just a second. I will just what will happen if we don't use bonding agent during reconcrete on existing concrete as bonding is so costly? And what is the alternative process that can difficult to read this question.
Let's skip. This has nothing to do with the subject of the presentations.
Right.
Let's not go there.
If we use water with high iron concentration, does it have any effect on strength of concrete?
Say that one more time. Read that.
If we use water with high iron concentration,
Iron concentration.
yeah.
I see.
So does it have any effect on strength of concrete?
Dr. Rakib may be more competent than I am.
No, it is preferable if you have water which is portable or palatable.
Yes.
So that is required. Now, higher iron concentration water is, from environmental point of view, is not portable. So from that point of view, but in terms of like concrete strength, we don't have any specific result on that. That a higher iron concentration does it impact the concrete strength in a detrimental way? We don't have any particular result on that, but usually it doesn't, as far as we found. So
No,
preferably we should use potable water, but if that is not, Dr. Ghosh, if you have
no,
anything
you
to add.
hit the right point. If water is, as I said, if water is not drinkable, you should not use it in concrete making. And from that point of view, high iron concentration will be ruled out. What the detrimental effects are, I do not know. As Dr. Rakib said, I don't know that there is experimentation available. Uh, and in the note, you see there is an ASTM standard now for water that you can use in concrete making. You can look that up, and that may tell you about a specific restriction. I do not know. But that will be your source. The key thing that Dr. Rakib hit rightly is that a high iron concentration will make water undrinkable, in which case you cannot use it in concrete making.
Thank you, Dr. Ghosh. So the next question is an expansion joint a consideration for RC structure applicable in Bangladesh on the basis of weather?
Expansion joints, I don't know why Bangladesh will be. Expansion joints are expansion joints, but let me say something very general about expansion joints. Expansion joints are a pain in the neck to maintain. Expansion joints are a gap that you keep for very many reasons, between structures or between portions of structures. This gap has to be maintained through the lifetime of the structure, and that is a tall order because there will be many things spilling out. It requires maintenance through the life of the structure. So we are more and more getting away from these so-called expansion joints. It used to be when we wanted to. So the most common use was to keep provision for shrinkage. Okay, so as I said, as concrete shrinks, if the shrinkage is restrained, you will have problems. So we did not cast too much of a length of concrete at the same time, because then we would have to deal with very significant amounts of shortening of concrete. But then we came up with these so-called pore strips. So we cast a length of concrete, then keep a gap, then then the reinforcement continues, but we do not continuously cast the concrete. We keep gaps at a certain spacing. And after the shrinkage has taken place, we come back and fill in the gaps. So there is literature on pore strips, how to do them properly, and if with the installation of proper pore strips, we have successfully cast 450, even 500 feet of concrete in one casting, thereby eliminating the need for expansion joints. Okay. Now, if you want to prevent hammering of two wings of a structure or two structures that are very close to each other in an earthquake situation, you will have to have a gap that you may call it a seismic joint expansion or whatever, I don't know what it would be called. That gap has to be maintained. And that becomes, again, the problem with expansion joints is maintaining the gap that you have decided to keep. And that, whether that is more of a problem in Bangladesh than in other places, I do not know. But that is always the challenge, why we try to avoid expansion joints pretty much at all costs. Long answer.
Thank you, Dr. Ghosh. So the next question is, what is the definition of air entrained concrete? Can we consider our normal concrete as air entrained?
Normal concrete is not air entrained. There are two terms. There is entrained air and there is entrapped air. Entrapped air is bad. Entrained air is good. Okay, the idea of entrained air is very, very small air bubbles that are well distributed through the mass of the concrete. And these are created by mixing, by putting air entraining admixtures in the mix while the concrete is being mixed. The role of these tiny air bubbles is when concrete volume changes. So freezing means the concrete volume decreases, thawing means the concrete volume increases. When the concrete volume wants to increase, in the absence of these air bubbles, there will be distress in the concrete. The tiny air bubbles make room for this expansion. Okay, so they are vital in a freeze-thaw situation. Entrapped air, on the other hand, which is not entrapped air, is common in concrete that is not properly placed, and those are much bigger pockets of air, and those take away from the strength of concrete. Where there is air, there is no compressive strength, obviously. So when you ask, is concrete naturally air entrained? No. But if concrete is not done properly, then there is typically entrapped air in it, and the entrapped air will decrease the strength, will take away from appearance. It may cause other problems. Entrapped air is bad. Entrained air you do not get for free naturally. No, there is no way. You either have to have air entraining admixture in the cement itself, or you have to add air entraining admixture while the concrete is being mixed.
Thank you, Dr. Ghosh. So it's almost 11. So a couple of questions. So shall we take?
Maybe
Or
one or two more.
okay. So ASTM A706
Mm,
allows grade 550W, that is 80 grade
mm,
reinforcement.
mm,
But BNBC 2020 imposes restriction on 80 grade in high seismic zone.
mm.
Can you kindly explain why?
I can easily explain why. we, it is because BNBC is based on old codes and specifications. So once it is, so it used to be. It used to be reinforcement strength was limited to 60 ksi, but not anymore. This is a later development. In 31819, we will allow not only grade 80 but grade 100 reinforcement in many applications. But for you, that is in the future when BNBC is updated to later editions of ACI 318. You will see this permission coming in. So the explanation is that 318 is based, BNBC 2020 is based on 31808, which referenced an older edition of ASTM A706, where grade 80 reinforcement was simply not there.
Thank you, Dr. Ghosh. Yeah, a couple of them more of them like mentioned that 500 W bars are something that is more available, like it's available more in the market of Bangladesh than
Yes,
420 V bars.
yes.
So that's why this question
So
is coming.
so the restriction is on seismic applications. I talked to Dr. Rakib about this yesterday. Yeah, apparently this grade 500, which is 72.5 KSI, is in wide use. There is no reason not to use it unless it is seismic design category D, E, and F, and D. The newer parts of Dhaka on less competent soil, D is not going to be uncommon, but anyway, other than D, there is no problem with there is no restriction on the higher strength reinforcement. But Dr. Rakib mentioned that the government projects, PWD, does not allow the grade 500, very likely because of the seismic restriction. So anyway, unless the bottom line is, unless you are designing structural members that are part of the seismic force resisting system of a structure assigned to design category D and above. I said these things quickly but very carefully. Unless you are designing a structural member that is part of the seismic force resisting system of a structure assigned to seismic design category D or higher, there is no restriction on your reinforcement, and so you should feel free to use grade 500 reinforcement. If it is a seismic force resisting member design category D structure, then you hit the restriction, and then you have to look for something else.
Okay, thank you, Dr. Ghosh. So I think freezing and thawing effects, you talked about it during the presentation.
Say that
So
again.
there's one question that are freezing and thawing effects considerable for concrete making in Bangladesh?
No, freezing thawing, to the best of my knowledge, is not your problem. No.
Right.
No.
And what if an RCC beam is subjected to axial tension and flexure? Is there any special consideration for designing? It's a very general question.
Axial tension and flexure.
Yeah, axial tension and flexure.
Well, there is nothing special. The entire tension has to be taken by reinforcement. That's what it amounts to. Concrete cannot be counted on to carry tension. So the direct tension as well as the flexural tension has to be resisted by reinforcement. So, so that's what it is. You will have to have a lot of reinforcement in that member.
Right. Most of the other questions have been answered. There is one big question that was very specific. So this question can be the last question for today's session.
Okay.
Yeah.
Okay.
So a retaining RC wall is to be constructed for a mounted storage tank, which is supposed to be 120 meters long and 7 meters high. Is it necessary to provide any construction joint for the retaining wall? If we want to control the deflection against lateral loads, what should be done to control the deflection? And is it possible to? It's a very big question. I've already assigned it to you.
No,
But
this kind of a question is kind of difficult to know.
yeah, it's difficult to answer
Uh,
right away.
yeah.
I think other questions, more or less, they are very general questions. Those things Dr. Ghosh have already like answered during the presentation. And if you look at the recording, if you have missed it by any chance, you can check the recording and you will find the answers to those questions, the other questions that are there. And
I think let us conclude here. One thing I wanted to mention at the beginning, after the first two sessions where we had 800 and some people attending, we are exceeding the limit of 1,000 set by WebEx. So some people want to attend and are unable to attend. Bodhi is trying to find solutions. So today and tomorrow, today obviously is done. Tomorrow it will be the same way. We will have no way of accommodating more. But we are trying to figure something out. So give us a chance. Hopefully we will succeed. But we are very, very glad at the interest level in these seminars that you are coming, that you are staying, that you are asking questions, and keep it this way. We will try to offer the best courses we can and answer as many questions as we can. Keep on coming, and we will try to solve the limitation of 1,000 people, which we never thought we would reach, but it's a good problem to have. Okay, thank you so very much.
Dr. Ghosh, I would just like to add to it.
Go ahead.
So today, as the webinars are progressing, the 1,000 limit is like it's being crossed like within couple of minutes. That's it. Like so that is not something that we can control, and we have checked other platforms. The 1,000 is the limit that most of the platforms, all of them, they have the 1,000 participants as a limit. So right now, as an interim solution, what I have done is that if you cannot attend the webinar because of the because the webinar room is full, then you can of course watch the recording later and still access the quiz if you have tried logging. If you have tried, if you have made an attempt to enter the webinar room. So that is being done as a temporary solution, and as Dr. Ghosh mentioned that we will try to find out some better solution, because of course a live webinar is always better than a recorded session. So yeah, so please bear with us and uh, participate in the upcoming webinars.
Yeah. As I said, we never anticipated hitting 1,000. So, but again, it's a good problem to have. Yeah. Thank you so much. Thanks a lot to Bodhi. He is actually making these things happen. I think we should all be grateful.